SwayamPrabha. Digital India. Educated India.
Okay, back. This is the very final part of the hydrogen embrittlement. I like a lot hydrogen. It's a very interesting and puzzling and an exciting topic, so I like to talk about it, but I think it's been enough. So we could come back to the phase field. And in order to make the transition to the phase field a bit smoother, I thought maybe I'll tell you a little bit about a couple of case studies that we've done that I think will hopefully be of interest to both experimentalists and computational people. Where we talk about hydrogen and phase field, but less about the mechanisms, more about experiments and what happens in there and so on. And then after I take these two, we could take a break, or we'll see how we're done, and then we move into the multiphysics. So this case two studies is something that we published last year, and the idea was to evaluate the suitability of the single-edge notch tension samples, and this was more a study related to, I guess, operations of oil and gas industry. So it's more what they call sulfide stress cracking, which is still hydrogen embrittlement phenomena, but it's a phenomena that you get in H2S environments. And H2S environments are environments where you have a lot of hydrogen, so it's pretty bad, but at the same time there's other things happening, so it's a bit more complicated. And this is the test that the industry does, but the industry has a lot of questions about this test. So this is the test they do to certified components for these aggressive H2S environments. But they have a lot of questions about this test. They don't really understand very well. There's two tests that they do effectively, the single edge notch tension and the double cantilever beam. And this is work, by the way, with Cupertino Maleros and with Tushar Mandal, who's now in IIT Bombay. And he's finishing up this paper, so I'll show some ongoing results of the double cantilever beam, but this one is already out. And the idea is, the industry has these two tests. They don't know which one is more convenient to use. They don't really know what the duration of the test should be, but basically they want the simplest test possible to certify the behavior of these components in these aggressive environments. This one they prefer a bit more, the double cantilever beam, because there they put a wedge, and then they leave. It takes more time, but they just leave the sample in an aggressive environment with the wedge, and a technician can leave it there. You can have 50 at the same time, and you leave and go back and take a look at it later. Well, the same, you normally apply an increasing load and so on, so it's a bit more, you need a mechanical testing machine, and so it's a bit more complicated. But yeah, there's a bit of discussion among that community, and the standards offer both options, and people are discussing which one is more convenient. So we try to use these methods to see if we can learn a little bit more about this. We did an experimental campaign on martensitic steel, C1110. It's a low alloy steel grade. It's a martensitic microstructure. We did two types of experiments. We did the constant load single edge notch tension, and then the DCB, which we'll discuss later. And we did permeation experiments as well, because one of the tricky parts here is to understand what is the hydrogen concentration that are happening there. And then we did, of course, a coupled deformation diffusion fracture model based on those phase field models that I showed you before. So first, starting with the permeation. So the permeation is what I explained to you on the previous day. So you have an electrolyte where you have the Bolmer, Hurwitz-Tafel, and Harovsky-Tafel and Bolmer reactions. Then you have an absorption of hydrogen, and then you measure basically how long the hydrogen takes to cross. You can see here, by the way, the picture of the permeation tests that were done. So you have a solution here, in this case with H2S. It's a bit more complicated solution that we normally do in the lab. You have a membrane of your material, and then you have some sort of an oblique surface where you measure the hydrogen coming on the other side. And this is what you see. And this is quite different. You remember that I showed you some permeation tests before, and all the permeation tests that I showed you before, when you plot the permeation current versus time, we're all looking something like this. There was a bit of a scatter, but they're all looking something like this. So it's growing, and then eventually you get some sort of steady state. Here you can see that it's a bit different. So the thing is going up initially, but then something happens and then it goes down. And this is basically the fact that you form an oxide. So it's a bit, and by the way, this is for various H2S concentrations. So the problem is that with this H2S is a poison. It's a combination poison, so it means that you get much more hydrogen into your metal than we normally would do, because it slows down the recombination reaction, so there's less hydrogen. So basically when you generate hydrogen, remember I mentioned that hydrogen actually doesn't want to enter your metal. Hydrogen wants to go away from your metal. So hydrogen would like to recombine into a molecule and then just leave. Some hydrogen comes in. H2S is a poisoning that it slows down the process in which hydrogen recombines and goes away, and therefore more hydrogen comes in. So that's why traditionally hydrogen embrittlement was a big problem for H2S environments. It still is, but the first times we started to be worried from an industrial perspective on hydrogen, even though we were working with materials that were not very susceptible, was the fact that we had this big amount of hydrogen coming in. So there's a lot of hydrogen coming in, but then something happens. You generate an oxide, and you can see the amount of hydrogen you have is coming down. So something is happening there. And this is, by the way, if you zoom in, you see the behavior that you would expect in a permeation test. So hydrogen is coming in, and this allows you to measure a diffusion coefficient. But then at some point something happens, and the hydrogen starts going down. And basically you see it experimentally. You form a corrosion product layer, so you have some sort of oxide that slows corrosion, and then the absorption kinetics. So there's something forming at the surface that is basically preventing hydrogen from coming in.
So
Yeah. T is time, sorry. So you measure hydrogen as a function of time, and normally is something like this. So this is current versus time. So you see, hydrogen eventually near to steady state. So initially you have no hydrogen on the other side, all the hydrogen on the inside. You're measuring things on the outer side, no hydrogen. Eventually you start raising the hydrogen, and then eventually you get a steady state. But here, you do get the steady state, but then something happens. You form these corrosion products, and things go down. So the hydrogen that you have in your surface must be going down, because on the exit surface where you measure things, you don't see hydrogen coming out. So the hydrogen is not entering your metal for some reason, or it's less and less entering.
So, but how is it possible, for 100% H2S and 10% H2S at a certain point at say 60 hours, the 10% H2S concentration is leading the 100% one? If you see
Why did those lines cross?
exactly.
So I think initially you see the expected behavior. So the more H2S, the more that you generate, that you slow the recombination reaction, so the more hydrogen you bring in. Then what happens after that is a bit complicated, because the percentage of H2S will also govern how much of those corrosion products you form and so on. So I guess what we are seeing here is that by increasing your H2S percentage, you are forming more of those reactions, those corrosion products. Those things don't happen if you don't have H2S. So that you are forming more of those corrosion products, and therefore you're blocking. So whether H2S is good or bad, I guess depends on. Is very bad at the beginning. Something's wrong. Okay, you're not seeing me there. No worries. So I guess at the beginning, H2S is bad because more hydrogen is coming in. But then later it might be even good in the sense that it's generating so much of these corrosion products that you're actually slowing down the hydrogen
Would
uptake.
have been done on some of the anode, right? The target material would be which metal?
These are experiments on this martensitic steel. This is a high-strength martensitic steel. But I mean, all these kind of oil and gas alloys are of relevance here. And this seems to agree with what we see in the experiments. So there's some classic experiments by Turnbull and by other people, and they measure some changes. There's a different pH, so it's not 100% comparable, but you see a difference in the hydrogen concentration with the H2S. So an increase in hydrogen concentration with H2S. Again, when we think about the first stage, before we block things from coming in. So then what we did to do is we did the fracture experiments, the scent experiment. So this is single edge notch tension sample. So you have a plate like this. You induce a crack here. You do some sort of fatigue pre-cracking. And then you basically introduce a solution with various amounts of H2S. You hold your load constant, and you wait. And the standard tells you need to wait for 720 hours. And this is a question we wanted to answer, because the industry partners weren't sure how many hours they needed to wait. The standard says 700 hours, but this is a long test. And they said, do we actually need to wait 700 hours? How much does it change, and so forth? And then, of course, you can get the stress intensity factor as a function of the applied load. And for the single edge notch tension, we know how the stress intensity factor relates to applied load since a century ago, maybe based on simple analytics. But depending on how you clamp your sample, it might be a small of an effect. So a lot of people have worked on developing a bit more, using finite elements, a bit more rigorous relationships. But it's not important for the time being. And then what you see, well, if you need to see if your scent passed or not passed. So a case that will pass, you don't see, you have a ductal fracture. One that it failed, you see quasi-cleavage fracture morphology. So this is not a component that you want to put in service, basically. That's the idea. And then the phase field model is very similar to the ones we discussed before. So it's an elastoplastic phase field fracture model with hydrogen. So you have an equation for the transport of hydrogen. you have a stress strain behavior. So we did a uniaxial tension test. We fitted that. We have a driving force that is 10% of the plastic work plus the elastic work. And the toughness degradation with hydrogen, in this case, we have a lot of data from the literature for this material, so we just fitted the data from the literature. We didn't take the atomistic approach, so to say. So this is the kind of test that we do. You see here is a constant load test, so eventually you see your crack growing, and at some point your crack stops. So this is what you measure. So this is the hydrogen concentration. Again, it's important to capture how the hydrogen concentration follows the crack. You can see that it's happening there. So this is the crack growth. This is the hydrogen concentration. And this is a 2D problem, boundary value problem. And what is important is that the hydrogen concentration that we prescribe on the surface is the one we measure from the permeation test. So you can see here, it goes up initially, but then it goes down. And I mean, we had to take this as an approximation. I think it's the best we could do. One could argue that maybe what you measure in a permeation test is not exactly what you see ahead of a crack, and so there's other things that ideally we'll have to explore. But it's the best we could do with the resources that we had at that time. The H2S phenomena is not fully understood also from an electrochemical perspective, so it was not easy. But there is work to do. If someone gave me infinite resources, you can see that clearly one aspect to improve is this one, because this is what we see on the permeation test. When we have a clean surface, we expose the material to hydrogen and it goes down. And this is probably fine for here. Whether this applies here, I don't know. It's an approximation of what happens ahead of a crack. But anyway, this is the boundary condition. And this is what we saw, basically. This is the 100% H2S. So this is the K applied and the time to failure. So this experimental load, so you see that if you apply a sufficiently low load, no failure happens after 710 hours, which is the limit, then they stop the test. So these arrows mean I stopped the test because failure wasn't happening. And you can see that both experiments and modeling seem to agree quite well. So if we have a big applied load, then fracture happens in both the experiment and the load, more or less at the same time. And then eventually there's this regime where the experiments show a bit of a scatter, but the experiments show that between 23 and 25 megapascals per meter, we have this transition from failure happening in 720 hours, failure not happening. In the simulations, we get a threshold of 23 megapascals per meter. Below that, we see things not failing. I should say, this is what people in the industry are a bit, puzzled about. In a way, not puzzled, but worried about. So they have a bit of a scatter here. They see they do this test. All the tests fail quite early. In all the experiments fail for them in 48 hours. So some of them will say, oh, why don't we just stop the test after 48 hours? We save a lot of money. We need to do many of these certification tests. Why don't we stop the test after 48 hours? This is what some people would like to do. But then at the same time, it's a bit of a challenge to do that, because you can see this guy failed very soon, but this guy didn't fail. And the change in load is very, very small. So the industry is worried. What if I had waited a bit more, maybe this guy will fail? So they don't really know what's happening. The good thing is that it seems that, our numerics seem to be in good agreement with experiments. So that's a good indication. So now we can interrogate the numerics. And this is, by the way, for the 7%. For the 7% H2S, they had much more scatter in the experiments. The experiments, again, are the circles. The open circles, you get significant scatter. So these ones fail quite early, but none of them, now they're failing later. Now they're failing in 200 hours. So these ones failed quite early. This one didn't fail. This one didn't fail. So there's plenty of scatter in the experiment. So now they're a bit worried. This problem is much more problematic for them. They don't understand why this one failed, why this one didn't fail after 700 hours, why this one failed after 100 hours. So somehow there's no correlation between load, time to failure, and so on and so forth. So this is a bit problematic for them. The numerics are a bit more clean. They seem to be more or less in agreement, but the numerics are of course cleaner in the sense that we don't have the scatter intrinsic to an experiment, so we do get that if you go below 34 megapascals per meter, no failure happens. Well, the experiment, we think the threshold is below 30 and 34, with some points even outside of that. So there's a bit of a scatter there.
What is the difference between KIC and KITH?
So it's basically it's a constant load test, so whenever your crack stops, you can measure the K that corresponds to that crack length and that applied load. And that gives you the KTH, yeah. But I think KTH is defined as the load at which, below which threshold, you will not see any damage whatsoever. Above, you will see it. So this the experiments that fail versus not fail. So then they use that for design. So then they say, okay, my KTH is 30. I make sure that in my component I never exceed 30.
KTH should be more than KIC, no? Like once the crack is initiated, then only it will stop after some time. So
Well, I think for this case it's simpler you think of it as K1C. Think of a K1C. It's used as a K1C criteria. We don't look into subcritical crack growth much in this case. Yeah. So then we use the experiments to interrogate a bit the model. So I guess we saw that the model seems to agree with experiments, particularly for the 100% HUS. For the 7% HUS, there's a bit of a scatter with experiments, so it's a bit more difficult. So what we did is we interrogated the model. So first we said, okay, forget about the fracture. Let's look, first of all, what is the hydrogen distribution ahead of because one of the key questions is, how long should the test last? Should the test last 700 hours? Because all the failures happen relatively early, for example, in this case, all in 48 hours, but they still do tests of 700 hours. But at the same time, here they can see that some of them fail after 200 hours, oh, sorry, I'm going too fast. Some of them fail after 200 hours, and some of them that are supposed to be failed didn't fail, so they're a bit concerned about how long should they wait. So this 702 hours comes a bit out of the blue. So first we did some simulations of crack tip stress fields and hydrogen concentrations, and we wanted to know, okay, what happens in terms of hydrogen diffusion in these materials, how quickly you get a steady state, how quickly you get the peak hydrogen concentration. And you see the simulations here, so this is without any crack growth, and you see that more or less, the steady state, maybe you need 50 hours, but you see, after 10 hours, your hydrogen concentration is almost there. So really, the hydrogen distribution is very close to the steady state after roughly 10 hours. So, maybe 10 hours is all that you need to run your experiment, and not 700. But there's an effect of this protective layer. Remember, at some point you generate this oxide. And now so this is a case where we just basically simulate hydrogen transport, imposing a constant hydrogen concentration. But we know that the hydrogen concentration is not constant. The hydrogen concentration goes down with time. So we decided to then put that simulation, so simulate how the hydrogen concentration goes down in time. And we see this. Initially it's growing up to 22 hours or so, then we get some sort of growth. So 10 hours is here, 20 hours is but then it starts going down, actually. So 50, so this is not very realistic. We reach to a peak in 22 hours, but then in 22 hours, you see here, more or less this is 100, so this will be 20. In 22 hours, it starts going down. So the hydrogen concentration does increase, but then it starts going down. But anyway, the picture doesn't change. So if we think of just, hydrogen transport, the peak hydrogen transport is roughly attained after 10 hours. After 10 hours, if you assume that the HUS is not creating the oxide film, then it will increase a little bit, but very little. And then if you assume that it's creating an oxide field, it will increase a little, but then it will go down. So we see, roughly 10 hours seems to be the right time instead of 700 hours. But we still see some failures a bit experimentally, slightly after 10 hours, so we still need to figure out what happens. And then what we find out is that if you look at the toughness versus hydrogen concentration data for these materials, and then we look at the hydrogen concentrations that you get at the boundary and at the height of the crack, because we don't know, we must be somewhere. So for the 7%, we move between here and here. For the 100% hydrogen HUS, we move between here and here. So what you see is that, there could be small changes in hydrogen concentration as a function of time and as a function of the effect of this corrosive layer. But those small changes in hydrogen concentration will bring very little change in toughness in the 100% HUS, because we are close to the plateau, which means that those small changes are not going to change very much my result of my experiment. That's why I see the repeatability in the experiment. But in the case of 7% HUS, is the opposite effect. We see a big drop. We are in a regime where the slope is very high. So a tiny change in hydrogen concentration due to the fact that, we waited a few hours more, or because the barrier, the corrosion barrier, protected a bit more or a bit less my surface, is going to have a big change in toughness, and therefore that is what it brings the scatter that we see in these experiments. So this is what we are basically highlighting with the model. So just to maybe conclude that case study, and maybe we could do a break now at 25 to 10, so we come back at 11. Just to conclude, if you do permeation, then you can reveal that role that those corrosion products have in taking hydrogen ingress. You then take that permeation data as an input to your model, and then you can see what is the competition between hydrogen accumulating near your crack and hydrogen uptake being prevented by those corrosion products. So you have two time scales competing there. The time that it takes for the hydrogen to reach its maximum value on height of the crack, which we know is roughly 10 hours, and the crack for the product to be formed, which is 22 hours. So we know that the one that wins is the hydrogen concentration time. We use these facial simulations to predict virtually this KTH, this cracking threshold. We see that we can get that cracking threshold, so that's good news, in good agreement. And when finally we can explain the scatter in the experimental data based on the fact that we are in this regime where toughness is going to be very sensitive to hydrogen concentration, so therefore small changes due to these different corrosion products, different experiments will bring to those changes. And by the case that we have 200 hours, we're a bit puzzled with the experiment that failed at 200 hours. What happened in that experiment? The only thing that we can think of what could happen is that so we see that we get a steady state hydrogen in 20 hours, so what happens in 200 hours? The only thing we can think of is that maybe we get crack growth, intermittent crack growth, they see that in the experiment, and when your crack grows, the hydrogen is following your crack, so the competition between diffusion and crack growth, the hydrogen can get farther thanks to crack growth as opposed to an unstable cracking process. But the role that hydrogen plays when growing, I'll discuss it in a minute now in the context of the next case study. So maybe we can do a break and come back at 5 past. Okay, thank you. Okay, welcome back. So I've been told tomorrow at the coffee break we may do a group picture, so whoever survives until tomorrow at the coffee break will don't run away immediately after you hear the coffee stop, because we'll probably get all a group picture here. That's what I've been told. So just before we go back into phase field modeling, as I said, we have 2 case studies. This is the one we look into the scent. We are in the progress of working with the DCB, but that's taking us a bit more time because the DCB is a complicated problem where people worry about what should be the sample thickness. So they get experimental data that seems to depend on sample thickness. And they don't really understand that what happens because, we know that fracture toughness experiments depend on the thickness, but only if your samples are thin enough. If you're thick enough, you get you converge to a plain strain fracture toughness. So they suspect it has to do with the hydrogen uptake. Maybe if your test is not long enough, this is a different type of test. If your test is not long enough, maybe you get hydrogen coming in from the sides. So it's a bit of a discussion. So we're trying to answer those questions, running phase field models. Tushar is running those calculations. Livia did the experiments, and you see a little bit, basically a 3D crack growth. But again, it's taking some time. It's a bit more complicated problem than we thought at the beginning. And every time you want to do a new test, you need to run a 3D calculation, which is always a bit expensive. Particularly here because we need to model very long time scales with the hydrogen transient problem and so on. Okay, the other case study is related to the suitability of a slow strain rate test. And this was motivated by our experimental friends at the University of Virginia. They've been working with slow strain rates quite a lot. Those of you doing experiments, particularly in hydrogen, will know that slow strain rate tests are the norm. People love doing these experiments. They are maybe not as insightful as fracture experiments, but they are much cheaper, much easier to run. So then they're really popular among the community. And people will either do them this is basically a uniaxial tension test, either in a smooth or a notch sample. But you apply your loading rate very, very slowly, because then in this way you let the hydrogen diffuse, and therefore you measure then the time to failure, and then you compare materials based on that time to failure, and so on. So it doesn't give you fracture toughness, it doesn't give you properties that you can use in design, but it does give you a benchmark of how brittle your material is relative to others. So it's quite popular. However, the colleagues that we have at the UVA, they have been a bit critical of slow rate tests, and they were a bit puzzled by a number of things. So one thing is that, these are all experiments on nickel superalloys. These are types of nickel superalloys. So nickel has a very low diffusivity, as FCC, very low diffusivity. And this experiment is not experiments where you pre-charge all of your sample. You pre-charge maybe sometimes 24 hours or a couple of hours, and then you start loading. So basically, most of your sample is not exposed to hydrogen. Only the surface is exposed to hydrogen, and then hydrogen diffuses during the sample. And what they see is that this is the intergranular depth. So they look at the fracture surface and they see what areas have been embrittled. And eventually your crack is big enough that even it will just grow unstable even through ductile processes and so on. But you do see an embrittlement region, and this is the area where you see intergranular cracking. And they can see that they get relatively large intergranular depths. So they did some, remember that expression that we discussed before, this d equals 2dt. They know the diffusivity of the material, so they know more or less how long the hydrogen has to diffuse. And they figure out that, over the duration of the test, the hydrogen will only move a few microns. So they say, how can it possibly be that we see embrittlement over regions on the order of millimeters? What could possibly be happening there? One hypothesis that they wanted to test with our models is that hydrogen is not a failure process where you just pull and at some point failure happens, which is what people thought. Maybe you get a crack initiating, the crack grows slowly and carries the hydrogen with it, right? But if that happens, that will make this kind of test non-suitable, because then it's kind of a fracture test. You have a crack, it's a completely different story. You need some crack measurements. Do you have measures of crack initiation, crack growth? What do you care about? Failure? So that would make the crack unsuitable. So this was their hypothesis. So we wanted to test this. First, what we did was a numerical simulations of hydrogen transport. So what you see here is the hydrogen concentration normalized by the boundary. So this is the edge of my component. For the four materials that we considered, 4 types of nickel superalloys. This is the finite element predictions. They wanted to see whether the hydrostatic stress made a big difference, but they didn't. But anyway, this is the predictions with the solid line are for the real diffusivity of the material. This black dashed line is the degree of intergranular depth that they measure in the experiments. So they see that hydrogen has embrittled all of this distance, here all of this distance, all of this distance, all of this distance. But when you plot the hydrogen concentration, you can see that it doesn't get any farther than there. First of all, you may need a minimum hydrogen concentration to embrittle things, so maybe your minimum is somewhere here, I don't know. But not only you need a minimum, but it's basically 0. So how can this happen, right? And we even tried, because some people argue maybe hydrogen moves faster through grain boundaries or other things, so we try increasing the diffusivity 10 times, which is kind of a very upper limit. We don't even see any of that in permeation, so probably it's much smaller than that. But we try increasing 10 times, and this is the color dashed line. And you see also, even increasing 10 times the diffusivity to account for uncertainties in diffusivity, we don't really get there. So something must be happening. There's a reason why hydrogen is stuck here, but embrittles a piece of material that is somewhere there. So the hypothesis is that maybe early cracking would occur. So we tried to figure out if we can learn from that from the model. And then one aspect that is critical in that case is that, this is a slide I just added now last minute because I thought it would be useful, is that your phase field model needs to capture how, as the phase field grows, as the crack grows, the hydrogen concentration follows. And it won't follow if you pre-charge your sample and are running a test in an inert environment. But if you're running a test in a hydrogen-containing environment, the hydrogen must, of course, follow. And we have 2 ways of enforcing this. One is through a penalty approach. So whenever you're solving for your hydrogen concentration, you have basically what you want to do is you make sure that in certain regions, let's assume that you have a hydrogen concentration from the environment, you are solving for C. So you have a penalty approach. So you have a very large term where you, depending on the phase field, you change the solution or your stiffness matrix and residual so that eventually the solution becomes this. This is one possibility. This is actually what we did in this paper. The other approach that in time we found much more straightforward to use is to use a situation where you basically define your diffusivity. Let's say you have a diffusivity, let's say effective or whatever, will be your normal diffusivity, and then some sort of a smooth function. It can be any function that you want, but some sort of function of the phase field and some sort of amplification factor. So basically, when you look at diffusivity versus phase field, and this is in the COMSOL Engineering Fracture Mechanics paper that we recently published, but this we found to be the most robust. So you are something like this, phase field is low, there's no cracking, your diffusivity is the same, but then as you approach phase field equal to 1, this grows in a quite smooth way to a value that is this effective. It could be 4 orders of magnitude larger. And then when you do that, because basically the diffusivity is enhanced here, the hydrogen here will just go quickly, and you capture this kind of behavior. You capture what you want to see. You want to capture as the crack grows, the hydrogen from the environment immediately fills that gap. So you can do that with this type of expressions or with a penalty approach. But this one is much more easier to implement, and it seems to work better. Yeah. The concentration is negative. Oh, I don't know if it's really negative. It shouldn't be negative, but so the blue region covers 0.56 to minus 0.1, so it could be something that has, if you have a node where you have a value that is very close to 0, so if, I don't know. So Abacus does some sort of average in between nodes. So I think this is the 75% that comes by default. So you may have an element like this, and maybe if you're, depends on what concentration I plot in. I think this one is maybe from the integration point quantities. So if you have an integration point here, if you have a gradient where this might be, I don't know, 0.5, this might be 0.1, then it might be that when you interpolate to the nodes and then you plot and do the average, maybe you end up with something that is tiny, but not. You shouldn't have negative concentrations. Yeah, I think it's just a numerical artifact coming from the extrapolation, because probably here I'm plotting the integration point quantities, and it's been extrapolated and averaged. So, but I wouldn't worry about that. No. It's very small numbers anyway, as you can see. Of course.
The concentrations that you have in terms of initial boundary conditions, what are they for this problem?
In this case, we reproduce the same as in the experiment. So we basically, the way they run their experiments is that they expose, I think they pre-charge for 2 hours, if I remember well. So they have the sample there. They expose it to it's an electrochemical environment. They have more or less quantified what hydrogen concentration belongs to that electrochemical environment through a permeation test. It's not perfect, but it's, and then they start pulling. So then we basically prescribe a hydrogen concentration here. We let the model run with our mechanical load for 2 hours, like they do, and then we start pulling. That's the idea. Yeah.
If you go to your actual results, the next slide, on there, what is the domain size relative to the sample, the experimental sample that one is looking at? Is it very near to the crack tip that you're modeling in?
This one?
Yeah, in the space field experiment, or is it accounting for?
Well, we model the entire sample. I don't remember. So this figure is just assumed to show the fact that but we model the entire sample, and this is, I don't know, maybe we can figure out from the notch size. You can see more or less the curvature. So I'm plotting zooming in somewhere here.
No worries. So then the question that I have is, if you look at the concentration, right, the range of concentration, in the interior, the bulk of the specimen, it's 0, is it? The
Yeah.
concentration is roughly 0. But shouldn't you expect that there would be some lattice concentration still there if I have achieved steady state diffusion for the entire concentration?
But we never achieve steady state diffusion because these are nickel alloys, so the diffusivity is super low.
Okay.
So you actually only get very little hydrogen uptake. This is what actually worries them, because they say, okay, how can it be? So if you look at the diffusion, this is over the full time of the test. This is the hydrogen depth. So very little hydrogen came in. Only the surface has hydrogen, but they see in the granular depths embrittlement regions that are very, very large. So this is what puzzles them, because these SSRTs are used for all materials. So for high diffusivity material, ferritic steels, then I mean within the time of the test you do get quite widespread.
So depending on the geometry of the specimen and what the material diffusivity is, then you have not reached steady state in that.
Exactly. Yeah. But in these nickel alloys, in order to get, I mean, they try to make them small, but you still need to do millimeter. You need to grip them and so on. You cannot do tiny samples. So this one's for a steady state in these nickel alloys, you may have to wait a couple of months or something. So it's very low diffusivity. It's 10 to the minus 14 and so on. So it's quite a So then the people still do the test, and they see a lot of embrittlement. So they were thinking, okay, the test seems fine from that perspective, but how can it be that? So this is the outcome. This is what you see the simulation, and this is the simulation after the end of the test. It's a slow rain test, so it still takes hours. It's not a quick test, but still you see, this very very little uptake of hydrogen.
What was the environment that this experiment was performed in?
This is an electrochemical environment. I think it's sodium chloride environment. Well, it doesn't really matter that much, but it's, they apply a potential, negative potential. They apply cathodic protection. So this is the most. I think this is the most used test in the hydrogen community. Slow strain rate test in an electrochemical environment, because it's the easiest to do when you think of mechanical and hydrogen. You need a cell, but otherwise it's straightforward. You don't have to, keeping track of where the crack grows is a bit more complicated. You need some DCPD and so on. So this is the simplest one. So this is very, very popular. It still is, I think, by far the most popular one. But the challenge is that one. In low diffusivity materials, unless you do your experiment over months, which no one does, then you have this problem where you don't have a lot of hydrogen coming in. But you still see the embrittlement. So, people, this is what puzzled these guys. And the hypothesis we had is maybe you get a bit of cracking, and then the crack follows, the hydrogen follows the crack. Because the electrolyte will immediately enter that crack, and therefore you get the crack exposure. That is the thought. So we tried to do these simulations. So first we started actually simulating the ductile failure. So we said the case in air for these 4 materials, we subjected we used the phase field model, and we modeled the ductile failure. So we're not resolving any micromechanisms, but it's an elastoplastic fracture model with some toughness and so on, so why not? And I think we calibrated with the experiment the toughness. We had toughness for this material, so it was a good agreement. So it was able to capture it's actually our prediction. So you can see this is the typical what you get in those experiments. You get load versus time, and basically you ramp up your load, and then eventually you get a drop in your load due to the failure. In this case, the failure for us happening in the center is due to necking and so on, and this is in agreement with what we saw in the experiments. So phase field predicts failure happening in the center of the sample, and we seem to be in good agreement in terms of when things fail. This is no hydrogen comes into the picture. The moment they bring hydrogen into the picture, they see failure happening in the edge, and we see exactly the same. And as you can see, we get a quite good agreement all across the board. So this is for a given applied potential. It's quite an aggressive one, so it introduces a lot of hydrogen in there. And you can see how the crack initiates. And the 2 interesting phenomena here is, first of all, the model can capture naturally the failure from ductile fracture with failure starting in the center, as they see in the experiment, to this failure at the edges and happening much earlier due to the embrittlement. So the model can capture the embrittlement well. The other key observation is that the model sees that we don't tell the model anything about when cracks need to start or grow or whatever. The model predicts some initiation of crack growth relatively early in the test. Depends how early, depends on the material, but relatively early in the test we see some initiation of crack growth. And then we see crack propagation, and eventually we see the crack failure in good agreement with experiments. And we actually try to change the environment and go from a more aggressive environment to a less aggressive environment. From the permeation test, we knew what was the hydrogen concentration, so we put that into the model. And as you can see, the model seems to have attained a very good agreement. So that was quite nice to see. So the model not only could capture the ductile phase, and then we put hydrogen and captures very well the hydrogen case, but we changed the hydrogen environment, and the model also captures well the time to failure, more or less. It's not perfect, but it's close enough, I would say. So this is good because it means that we trust the model. The model seems to be able to capture all the data that we have. And what the model is telling us here is that you have initiation of crack growth. And if you have initiation of crack growth, then this test is not valid. And the other problem that we found here is that then you don't really know what to do with this test, because even to rank materials is not very useful, because basically people rank materials based on the failure load. But you could have a material where cracking initiates first, but because it has lower diffusivity, the crack propagates more slowly, and therefore the time to failure happens later. But cracking initiates first, so depending on your problem, that initiation of cracking could be a problem. So yeah, we basically think that this explains, it's a model. We don't have clear experimental evidence. Although there's a group in Manchester that have shown by comparison fracture surfaces that indeed cracking initiates first, and doing some interrupted testing. So it seems that what the model predicted is being confirmed later by experiments. So the model is telling us that most likely crack initiation occurs, and therefore this will make so this explains the conundrum. This explains why hydrogen only enters a little bit, but brittle failure is seen over large distances. But also this tells you that this kind of approach is not a valid test. You need to do a proper fracture test.
The ratio to which it rises, right, the diffusivity. So does it show dependence on the final results?
The ratio?
Of which the DL rises from 1 to 4, right?
124. What changes to 124? Sorry, I missed that.
So the phase field wherever the parameter is 1. So where the diffusion coefficient is increased to some number, right?
Okay. So here, understand the boundary condition. So here we use the penalty boundary condition, but it has no influence on the result. So you just need to pick, when you deal with penalty boundary conditions, you have a penalty factor. If you are forcing the solution to become equal to this, to the environment, in a certain region. So basically what we want is, in this region here, I don't want my hydrogen concentration to be the solution of a transport problem. I want to enforce it to be the hydrogen concentration at the boundary. So I want this to be red. So the two ways you can do that is by adding a penalty factor into your equations. If your penalty factor is the larger it is, the more precisely you will capture this, but you will also bring more convergence issues. So there's a balance basically. You pick your value large enough that will give you what you expect to see, like you see here, but that it won't cause you convergence issues. A little bit the same goes for here. So you wanna, if you follow this approach, you wanna pick this. This only happens in phase field regions that are very high, so it doesn't affect your results. You wanna pick, the effects in the sense that it's capturing the hydrogen growing with the environment following, which is what happens in physics, but what value you pick here is not important. You need to pick a value that is big enough to see this, but not too big that will cause you convergence problems. I think that's the idea. So for us, for the order of magnitude increase seems to do the job. It doesn't give convergence issues, and we can see that the hydrogen is following the crack. That's the idea. Okay, then later we'll look at this problem in a different way. So this is a study that I did, the second paper, which was, it was not in corrosion science. I think it was International Journal of Hydrogen Energy. I need to change that. It was with a group in Spain, in Seville. So they were interested in looking at this problem from kind of resolving the microstructure. So they said, okay, what if we take a different approach to this? And because we're looking into this problem and another problem that was also quite interesting. What if we took a different approach to this? We assume that the phase field tells me whether I have ductile damage. The phase field is going to model ductile fracture only. And then I resolve my microstructure. I include, I do Voronoi tessellation and I put grains in there. And then I put cohesive elements in those grain boundaries. Because in this material, in other materials, how hydrogen interacts with the failure process still very much under debate. But in this nickel superalloys, it's very clear, you get intergranular crack. So then they said, okay, we put hydrogen there. The hydrogen is degraded with the hydrogen concentration. We have attraction separation law, it's degraded with concentration. And then the phase field just tells me whether I have ductile fracture. So then I have both things competing at the same time. And then I just run it and see which one happens first, whether ductile fracture or brittle failure. And then we run those experiments, and we got a very good agreement again with experiments. So this is for the four materials that I showed you before. This is in air. This is with very aggressive hydrogen concentration. Here, the Quisison model did not break. There was no hydrogen. The stresses were not big enough. So failure happened due to the phase field evolving, which represents in this case these microvoid ductile mechanisms. Here, those Quisison elements break, and it's not perfect, but again, it's in quite good agreement, I would argue, across a wide range of materials. They're not two different materials, as you say, but it's fine. And so this is again, it confirmed basically our expectations. It told us that we could see the cracking occurring like this. You can see this is an element of the simulation, so you see crack growth along the grain boundaries. So we again capture with this more macrostructural resolved model, we were able to capture how those cracks originated in grain boundaries when you brought the hydrogen in. We could see how those cracks propagated as the test continues, so that you get initiation of we confirm basically what we saw with the more crude macroscopic model.
How did you handle the binding energy in the grain boundaries?
This one we took. They had done some. I'm trying to remember. I think they did some TDS measurements on this one, and they took a value of 30 kilojoules per mole, which is.
I'm talking numerically. So did you have you gave binding energy only for the cohesive elements that you inserted to the grain boundary, or?
Okay, so very good question. So there's two ways of doing it, and now that we're doing a lot of crystal plasticity, we have various ways of doing it. Now you're resolving the grains, so you could think of it as a. I think that the way the people did it at the beginning, they basically had a. If you think of, you have a grain here and then another grain there. You could think of you are solving this with continuum bulk elements. So you see which is my bulk element closer to my interface. And then you say, okay, if this is my bulk element, I can use, and it has this concentration of lattice, I can use Oriani's equilibrium to tell me what is the occupancy of a trap with a given binding energy. That's one approach. The way we do it a bit now is a bit different. We have some sort of segregation energies and so on. It was not the case of this paper. This paper was the simple approach. I can show you later. We haven't published anything about that, but I think it's a bit more rigorous. And it's a bit more complicated as well, but a bit more rigorous to capture the transport to grain boundaries and so on. So we do have one paper published where we have some sort of permeation models with grain boundaries where we account for some segregation factors, so you can see the transport to grain boundary.
In principle, I can always say, hey, this particular element belongs to the grain boundary or near grain boundary.
Yeah, this is the approach here.
It will have a different binding energy, and the bulk of it will have, let's say, a different binding energy.
What we do now is we follow something like that. So we use the phase field to interpolate grain boundaries. So it's a different phase field. It's a initial phase field in a way, or we don't even evolve it. So it's just like an interpolation phase field. So at the beginning we say we use a phase field or any other interpolation function to describe grain boundaries, and therefore we can say, you know, the binding energy changes from the if I look at a graph like this, you could have a phase field that goes like this, and you can say the binding energy goes from this value to whatever bulk binding energy you have. So the change in activation energy from one to the other. This is more or less what we're doing right now. Yeah. So interpolating those numbers. Yeah. Not to have like a sharp, I guess you could have a sharp one as well, but yeah, this is it. Or instead of taking one row of elements, more like that you have yeah. Of course, there's a lot of questions in there. This is a very interesting scientific problem, because then what is I understand that grain boundaries are diffuse, but what is the thickness of a grain boundary? Can you resolve that in a continuum model? And there's a lot of tricks that the phase field microstructural community is playing with those things, because they have, for crystal growth and so on, they have tiny interfaces that they want to scale up in finite elements, so they have tricks to make sure that the energy is conserved, and they have various ways of solving for a bigger one but correcting so that the physical behavior corresponds to a smaller one in a way. So this is some of the things we're looking at now. Yeah. And then the last part of this study where we were looking at is a slightly different problem. So the group in the University of Virginia, they did some experiments, again with SSRTs, but that's not relevant here, on nickel. And they were trying to understand whether, at least on nickel, whether this kind of, they were trying to bring some light into the debate. In hydrogen, there's always this big debate about the mechanism. Some people argue whether it's a decohesion-driven mechanism or a plasticity-driven, maybe a combination of both, and that can change with environment, with the material, and so on. So what they did in nickel, they said, okay, we're going to run experiments at room temperature with and without hydrogen, and we're going to do experiments at very low cryogenic temperature, 77 K, with and without hydrogen. And if we do that, then we're going to look at the fracture surface and want to see whether we see embrittlement or not. And the reason of doing experiments at very low temperatures is that in those cases, there's no hydrogen diffusion and there's no hydrogen plasticity interactions. So the only thing that you have is hydrogen trapped in grain boundaries. So is the hydrogen in the grain boundaries enough to trigger the cohesion, or do we need extra mechanisms? And they saw that, so this is a seminal paper in the area, they saw that the hydrogen in the grain boundaries was enough to trigger embrittlement. So even at the 77 Kelvin, you put hydrogen, you see embrittlement mechanisms. So we saw we could capture that. So we reproduced this with this model, and indeed, you can see the agreement is relatively good. We were capturing that in the absence of hydrogen, we predict ductile fracture as driven by the phase field. When we put the hydrogen in, even changing the temperature, because this model you can change the temperature, everything, I don't have the equations here, everything are Arrhenius laws that you can change the temperature, you change those binding energies, you send the diffusivity, and we can see that we get also the qualitative and quantitatively the capture from mechanism to time to failure and stress strain curves, as you can see here. Okay, so that's all I had to say about hydrogen, or almost all. I think when we talk about multiphysics, I may have one result where we show you how to implement this in practice. So let me move into, there's a message in the chat, that's interesting. Oh, there are questions in the chat. I didn't realize that. Oh, there's people following online. Okay. 4 people following online, it seems. And there's a question, how can we decouple strain localization effects from true hydrogen distribution in SSRT when multiple mechanisms exist? What do we say about the dominant failure mode? Well, I mean, I guess the last example that we did is the most relevant one, right? So we are doing, people did experiments under very low cryogenic conditions, and in this way you can decouple this phenomena. You can also do it by playing with strain rates, but at low cryogenic conditions you can decouple this phenomena, and we saw that eventually it was all driven by embrittlement. Anyway, strain localization without hydrogen will not drive intergranular cracking as we saw later. But thank you for your question.